A2 Maths, differential equations. Alright, so you've seen things like this before, dy over dx equals 4x, or anything with dy over dx in. And what they're called is what's called differential equations. So you might have always referred to them as the gradient function or differentiation, but the actual technical name for something that's got a rate of change part in it, a dy over dx in this case, a change in y over change in x, is called a differential equation. And that includes ones where it is a second derivative. So when you've seen equations with d squared y over dx squared, that would still be a differential equation. Anything that's got a rate of change formula in it. Now, if I said to you, I've got that differential equation, could you work out the actual real equation for me, please? So the original equation. All right, so pause there, have a quick go yourselves. Okay, so you're quite rightly guessing that if you've differentiated and got 4x, how do you get back to the original equation? You would have to integrate. So if I look at this function just here, I differentiated it, I got 4x. How do I get back to the original function? I'd have to integrate 4x. Integration of 4x, of course, is 2x squared. And that makes sense because if I differentiated 2x squared, 2 comes to the front to make 4, power decreased by 1, back to 4x. So I can clearly see how to get from that differential equation just there to this equation just here, to the single y equation. Do not forget the plus c. The plus c is absolutely vital, the constant of integration. Because if as you know, if you look at this situation just here, and c was, let's say, for example, 10, and I differentiated it, that plus 10 would disappear, and I would still end up with that same differential equation, even if it was like minus 15. It would still be that same differential equation. So it's important to make sure you include the constant of integration, especially for this section of work. Okay, right, so I've got that equation just there. Now that equation is what's called a general solution. And the reason why it's a general solution is because I don't actually know what the constant of integration is. My two examples a minute ago was c could equal 10 or c could equal minus 15. Of course, there's an infinite set of answers it could equal. So because there is a massive amount of different situations it could be, then we call it a general solution. Now, if I give you an extra bit of information, so I'm telling you now that what I know is that this equation, this y equals 2x squared plus c, goes through the point 3, 23. So 3 for x, 23 for y. Could you find for me the solution now, please? Okay. All right, so let's see what you got then. So hopefully you substituted both of those into there and you worked out what the constant of integration was in this single situation. And the c value in this case worked out to be 5. When you substituted in 3 for x, squared is 9, times by 2, blah, 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 is 18, plus an extra 5 to get to 23. So I get down to this equation. Now that equation is not a general solution because it's only got the variables x and y. The c value has been calculated. So this is what we call a particular solution. So when I solve an integral, right, so when I solve a differential equation by using integration, the first thing that comes out is a general solution. And then what I could do is I could use an extra bit of information to change that general solution to what we call a particular solution. And a particular solution basically means that you have an equation which only has x's and y's as the variables. Okay, so make sure you pause, get down what you need for your notebooks. Right, so what I'd like you to do though, is I'd like you to think about how we find the general solution of 4xy. So that's a little bit more tricky. Right, the y's mess us up. So grab your notebooks, put that down in your notebooks, pause if you need to. Right, so when we come to solving a differential equation that's not so straightforward as the previous one, in this case it has x's and y's in it, then what we need to do is we need to look at a new technique. And the new technique is what we call separating the variables. This differential equation is called a separable equation. It means we should be able to separate out the x parts and the y parts. And then when I'm talking about separating them out, I'm including the dx and the dy. So those two can be separated out as well. Okay, now technically, mathematically, it's not quite right to times both sides by dx, but just for the reason of this, it makes it a lot easier to understand. So what we're looking at is, can you take that equation, can you rearrange it so all the x's are on this side of the equal sign and all the y's, including the dy, are on this side of the equation, or the other way around. Okay, right, so pause there, have a go yourselves while you take down those last bit of notes. Okay, so the first thing I'm going to do is, just to make it a little bit neater, I'm going to multiply by dx. So I've got that. So I'm almost there. I've got the y on this side, I've still got a y on that side. So let's get rid of that y and then I'll be sorted, because then I've just got x's on this side. So there we go. Divide by y gets me 1 over y dy equals 4x dx. So I'm sorted now. I've got all the y variables on one side, all the x's on the other. It doesn't matter which way around these two go, as long as you have all the x's on one side and all the y's on the other. Right, once I've got to this situation, what I can do now is I can just integrate both sides. So once I've actually separated out the x's and y's, I can just integrate both sides. And now that I can integrate this, I'm integrating a y function in terms of y, and on this side I'm integrating an x function in terms of x. So there's nothing difficult now. I just need to make sure I've got the integration skills, that could include parts or substitution, of course, to be able to solve these two integrals separately. Okay, and that's what we're going to look at next. So if I look at the integration of 4x, that's not too bad because I've just done that. I know that goes to 2x squared. The integration of 1 over y, and this is one that you need to learn off by heart, all right, because you know that when you do y to the minus 1, it doesn't work when you try integrating it by increasing the power by 1, divide by that power. So 1 over y must go to something else. And of course, in this case, it is ln. All right, so the integration of 1 over y in this case will be ln y. That part is 2x squared. Notice that you don't need to put a constant integration of both sides. Just the one side, just put it on at the very end, is all you need. And the reason why you only need it on one side is because if you had a constant here, let's say you had plus c here and then plus k here, you could put those together and it would still be a constant value. So an example could be ln y plus 3, 2x squared plus 5, but if I take that 3 over this side, I end up with plus 2, and that's still a constant. It's still a number. So it's a lot easier not to worry about loads of separate constants floating around. Just put one at the very end of the equation. But it's very important you do not miss it out. So that's it done. I've got an equation there that's got y's and x's in. It's a general equation because I don't know what the c value is. That could be any number, but it's a general solution to that differential equation. What I want to do though to finish it off is put it what we call explicitly to do with y. So in other words, I want a y equals equation. So how do I do that? Well, the first thing I would do is, obviously, to get rid of ln, I would use the exponential function. So y equals the exponential function 2x squared plus c. And there we go, I'm sorted. What often happens though is that this equation just here, e to the 2x squared plus c, this constant here can actually be written a lot neater rather than up there. Right, according to laws of indices, sorry, I can separate out two things where the power is added into two things times together. So for example, that times by e to the power c is exactly the same as e to the power 2x squared plus c. So just make sure you're happy with that. Just a bit using the laws of indices backwards there. So I've separated it out into this. Now, why would I do that? Well, I know, because I can manipulate constants, I can play with constants, that e to the c is just going to be a constant. Because c is a constant, e to the power c is just a constant. Now I can't just change that to c again, because it needs a new letter, because e to the c is going to be different to c. But what I can do is I can just change that for a different letter, a different constant value. And in this case, it's very standard to use the letter capital A. So we end up with y equals capital A, that's e to the c, e to the 2x squared. Now that is correct, that line just there, but this line here is a lot neater, and you're more likely to see that popping up in exam questions, having it in that form. Okay, but the truth is those are all different forms of this general solution to that differential equation. You've done the hard work there doing the separating variables and integrating it, then you're just playing with constants on these parts. Okay, so let's get our notebooks. Just get this question down in your notebooks. I'm looking at finding the general solution to that differential equation just there, and the particular solution using these two values here. So in your notebooks, if you get that down, and then maybe have a go yourself, maybe you want to just try working through my previous example, and then I'll go through the answer with you once you've unpaused. Okay, so let's have a look then. So the first thing I want to do is think about separating out these variables. And to me, it doesn't seem too bad. Obviously, I want to get that y squared multiplied by y squared to get up here, and the dx from down there, I can times and get it on this side. So I can rearrange it, and that is going to become that equation just there. Once I've separated out my variables, all the y's on one side, all the x's including the dx on the other side, I can then just stick an integration sign in front of both of them, and there we go, I'm sorted. What I need to do now is use my integration skills to integrate both of these. Neither of them look too bad. Increase the power by 1, divide by the new power, same there, same there. So I end up with y cubed over 3. 4x goes to 2x squared, 3 goes to 3x, and do not forget that constant of integration only on one side, just chucked in the end. If you had it attached to this side, not a problem at all. It's the same correct answer. So there we go. I've managed to find a general solution. Job done. I don't need to do anything more. You might want to just multiply by 3 and neaten it up, but you don't have to. Okay, so we'll look at what I've done there though. It's worth just noting, because I've times by 3, I've neatened that part up to get y cubed. Okay, the 2 obviously goes to 6 when I times that by 3. The 3 obviously goes to 9 when I times by 3. And if you've written 3k, just 3c just there, there's absolutely nothing wrong with that answer. C is times by 3 as well, so you'd have 3c. Now 3c is a constant. So what I'm doing is I'm just manipulating my constants to show that it's just good practice. Instead of writing 3c, just use a different letter and saying this is a new constant just here. Yes, k is 3 lots of c, but it doesn't matter. Okay, now you've got this new constant, that's the one you're playing with. Right, so I've got my general solution. Now I could potentially be thinking about what to do next. So if I look at the next situation, okay, I've got my general solution. How do I get my particular solution? I just need to put in these two values to work out the value k. Okay, so 1 to 3, substitute them in. All right, y equals 3 when x equals 1. Bit of rearranging, and out pops k equals 12. So now I've got k equals 12. I can rewrite my equation, okay, and get the particular solution. And there we go. Y cubed equals 3x squared plus 9x plus 12, sorry. So once if I wanted to, I could work out that previous c value, but there's absolutely no point at all. Once you replace the constant with a new constant, you can almost forget your previous constant values. You don't need to worry about them. And there we go. There's my final particular solution to this differential equation. Okay, so on exercise 12.2, there's quite a lot of work to do. It's a good idea to practice as many differential equations as you can. All right, you only get this single type of differential equations, the ones where you have to separate the variable. So it's good practice just to make sure that you're used to doing that skill. I've started with the differential equation and then rearranging and getting the general solution out. Okay, now pause there, have a go at the exercise, move on when you're ready. Okay, so if y is directly proportional to the variable x, you would write it as what? Or how would you write it? Okay, so maybe you've done it at school, something you might have done, and you might have seen this symbol before used in previous lessons. When we talk about proportionality, or something's proportional, we use this symbol just here. Okay, similar to the alpha sign. So y is proportional to x is how it would read. Okay, so in other words, if you had a situation where maybe x is just double what y is, those would be proportional. All right, because that would be 2, that would be 4, that would be 6, that would be 12, that would be 10, that would be 20. They're proportional to each other. They have that multiplying relationship. Okay, that's what it means to be proportional. Now, because you've got this multiplying relationship, it means that you can rewrite this as an equation rather than with proportionality symbol. So if I know that y is proportional to x, it means that y is some multiple of x. That's what it means, some constant multiple. All right, twice a lot, 2 lots of it, 3 lots of it, half of it. Doesn't matter what it is. We can rewrite it using an equal sign and a k value as that constant. Okay, so y is proportional to x and it is a k multiples of x. Okay, so I don't need to worry about proportionality symbols. I do need to worry about making a proportionality equal k. That's the key part. Okay, so let's just look at some other key language. If the variable y is directly proportional to the variable x to the power n, so does it matter if you had maybe a different function, like in this case x to the power n, some type of sort of polynomial function, for example? But does that change how we do proportionality? And the answer is no. We still got y is proportional to x to the power n. So rather than last time it was just y is proportional to x, this time it's proportional to, let's say, x squared. Okay, so if y is proportional to x squared, it means that y could be 2 lots of x squared or 3 lots of x squared. You can figure out how it's proportional, then you can figure out that constant multiplier. And because it's still a constant multiplier, I can change that proportionality symbol to an equals k. What about this one? So you might have seen those words. If y is inversely proportional to x to the n. So what does it mean to be inversely proportional then? Well, you'd be incorrect if you thought it was to do with being negative. We'll talk about when to use a negative symbol later. Now, if it's inversely proportional, it means that you are dividing by it rather than multiplying. So you're looking at 1 over x to the n rather than just proportional to x to the n. How could I change that proportionality symbol though? I can just replace it with an equals. And it's quite normal to put the k at the top, right, because it's just k times 1. But if you wrote y equals k lots of 1 over x to the n, it's the same answer. There's no difference to them at all. Okay, so I'd like you just to have a go at practicing some of these. Okay, so the number of boys is proportional to the number of girls. So how would you write that? How would you write that as an equation? That's what it's asking for. Okay, so pause there if you need more time. Right, let's have a quick look at what you did. The boys are proportional to girls. You didn't need that bit. So that means that the equation would be boys equals k lots of girls. And it's quite standard to use different letters. It's not always x and y, but if you was going to use x and y, make sure you clearly label which one's x and which one's y. X is the number of boys, y is the number of girls. Okay, so height is proportional to the square root of the width. So height is proportional to the square root of the width. So have a go at writing that one down and check it. Pause if you need to. Okay, so height is proportional to the square root of the width. What does that mean then? Well, that means that h is equal to k lots of the square root of w. Okay, so making sure you can write the equation is absolutely vital. Okay, so have a look at this one. Pause if you need to. Okay, so the area is inversely, right, we just done that a minute ago, so that's 1 over. So the area is inversely proportional to the square root of the radius. So area is proportional to the square of the radius. Read it right. So 1 over r squared. How do I write that as an equation then? Just stick the equals k in. Okay, a equals k lots of 1 over r squared is perfectly acceptable as well. The growth of x over time is proportional to x. Okay, so you want to pause there and have a good think about this one. Right, so there's a hint. The change in x over the change in time. The growth of x over time. So that's the change in the x value over the change in time. Now I know how we write change in x over time. I know how to write change in y over change in x. I write that as dy over dx. So if I'm looking at change in x over the change in time, I'm thinking dx over dt. Change in x over the change in time. And I know that's proportional to x itself. Okay, so that could be a situation is if it was the growth of x, if x is like a size, the bigger x is, the faster the rate of change. That makes sense if it's something like bacteria. If you've got a big amount of bacteria, the rate of change is a lot bigger than if you had a small amount of bacteria. So the rate of change is proportional to the size you started with. That's what it means. So yes, I could write that as an equation. But now I've got this equation, I want you to do something else. I want you to solve that differential equation. So from a single sentence, the growth of x over time is proportional to x, we've managed to get a differential equation, and now you're having to go at solving that equation. Okay, so pause there if you need more time. Right, let's see what you got then. So we've just rearranged it slightly. I've put the dx over that side. Yes, the x's need to go on the other side, so I rearrange it further. Notice the k value. If you wanted to take the k value with you to the other side, if you had 1 over kx, for example, that's fine. I've just made it a bit easier for myself and I've left that k value on that side. But it didn't make any difference. It can go with either. So 1 over x I know goes to ln x. The integration of a number in terms of time is just going to go to a number times time. K is a constant here. Don't want to see any k squareds over 2. We're not differentiating in terms of k. Sorry, integrating in terms of k. So be very careful. So that's just going to go to kt. Plus this extra constant of integration. Remember, the k value was from the proportionality. It wasn't a constant of integration. So I need this extra plus c. There we go. I've got my equation sorted out. I might need to do more work on that in a proper question, but we'll come back to that later. Right, so the rate of temperature decrease over time is proportional to the temperature squared. So pause there, have a go yourselves, and by all means go a bit further and have a go at solving the differential equation if you get a differential equation. Okay, so I'm reading the rate of temperature decrease over time. So that's a change in temperature over change in time. So temperature, I'm going to have as capital T. T is the temperature and lowercase t for time. So the change in temperature over the change in time is proportional to the temperature squared. So there we go. But what other key word is important in here? The word decrease. So I said a little while ago, I'll tell you when negatives come in. Negatives come in if you're talking about decrease or deceleration. If you're talking about sort of acceleration and deceleration. So you can put the minus sign in just there. It's decreasing. So therefore I put a minus sign in. So it's all about reading the question and making sure you can write the correct equation from the question. In this case, the correct differential equation. Right, can you have a go at solving that one then, please? So just pause there. Okay, so let's see what you did. Took the dt over, took the t squared over this side, potentially left the minus k where it was. Okay, so I've taken the minus out. I could have taken the k out as well if I wanted to. K is just a constant. So you don't just need to take the minus, you could take the entire k value in. And then you would definitely have the integration of 1 dt goes to just t. This side, no lun's in this case, because that's t to the minus 2. So that's going to go to the minus 1 divided by minus 1, which is where that part comes from. Don't forget that minus that comes from there and that minus there cancel out. Hence, we don't have any minus signs in our final answer. Okay, so have a go at this one. Population P increases over time T at a rate of 2 over P per hour. Okay, so just pause there. Have a quick go. Right, so the key part to this one is already telling you what the rate is per hour. Notice there's no mention of the word proportional. And so because there's no mention of the word proportional, this is not a proportionality question. We don't need to see any of that proportionality sign, and we don't need to write equals k lots or something. They're literally giving you the answer. They're saying to you the population, P, increases over time T. So I've got dP over dt. And I also know what dP over dt is equal to. It tells you it's 2 over P. So without proportionality words in there, don't start doing proportionality. It hasn't always got equals k in. That's it. There's my answer. Can you have a go at solving that differential equation then, please? Okay, pause if you haven't done already. Okay, so I'm timesing by P, timesing by dt, and I end up with that. Okay, so the integration of P, the integration of 2, P is going to go to P squared over 2, 2 is going to go to 2t plus this extra c value. So very well done if you got that. Yes, you can neaten it up further, but I'm not expecting you to do that just now. So have a go at this one. The height h of water in a tank decreases over time t at a rate of 3 root h per day. Again, picking out some of that key language, noticing the fact it doesn't mention proportionality. It's giving you a rate per day, so it's telling you already what the rate is. It's telling you what your gradient function is going to be. How do I write my gradient function? Change in height of the water tank over time. It's not always over time. We'll come to some of those later on, but generally they would be because things change over time. So the height of the water tank decreases over time. Let's say it's got a leak or someone's left the tap on, the amount of water in that water tank decreases over time. And it decreases depending on the actual height itself. All right, so if it's very high, maybe there's more pressure and more comes out. When it's very shallow, less pressure, less comes out. So the rate depends on h. Okay, so how do you write that? Change in height over change in time equals minus 3 root h. Okay, pause there, have a go at doing the differential equation yourself. Okay, so let's see what you got then. Yes, times by t, divide by minus 3 over h, or divide by just root h, sorry. Leave the 3 where it is, makes it a little bit easier. Again, there's nothing wrong with you taking the 3 under, but then you're dealing with thirds. Okay, so just be aware of that. Root h is h to the half, so 1 over root h is going to be h to the minus a half. You can integrate that yourselves. And that's where you're going to get 2 root h from equals minus 3t plus an extra constant of integration. Okay, so this is quite a big question, as you can see. This is an exam type question because there's a lot of words going in there, and this is quite standard when it comes to the differential equations questions. Differential equations come about very often when you're doing sort of university courses and things like that, because a lot of you scientists, engineers, anything like that will end up talking about rates of change. And the moment you mention rates of change, you're forming differential equations. So what the examiners are expecting you to do is understand how to go from real world problems like this one into being able to write equations and differential equations and then go on to solve them. Okay, so I'm going to pause there, give you a chance to get the question down, give you a chance to have a go yourselves, and then we'll have a look through the answers. Okay, so I'm going to start with the first one. I want to take some of these words that come up here in the model to estimate the population of a small island, write down a differential equation P and related to P and T. So let's start there. All right, I'll just drop the bottom two off. I'll come back to those in a minute. So in the model to estimate, it's assumed that the population P at time T years, sometimes they might trick you out and change between units. So I need to be careful. This one looks like it's being nice to us though. So the population T years after such a long time ago, 1991, is continuous variable, which increases at a rate proportional to p. Right, so the rate of change of p over t is proportional to p. So trying to cut out a lot of those words and trying to get a picture of what's actually going on. The population p at a rate after its continuous variable, which increases at a rate proportional to p. So it's talking about a rate of change just there. So I can write it down as dp over dt. So I can write that first bit down as a change in population over change in time is equal to some amount of the original population. So once I've got that, now what I can do is I can have a go at solving the differential equation. So in part B, that's what they're sort of talking about. They're talking about trying to get solving the differential equation to get some sort of particular solution. So what I'm going to do is just rearrange this equation first and get myself a particular a general solution, and then I can go on and potentially use this 50,000 to get a particular solution. So the first thing I'll do is just rearrange this. So I can maybe take the p over the other side, leave the k where it is, take the dt over. So I get 1 over p equals the integration of k in terms of time. Being very careful with that k, not doing anything silly with it, it's just a number. So what I end up with is ln p equals kt plus c. Noting that yes, I've done it. I've got an equation that links the population to time. I don't know what k and c are, but I'll figure those out soon. Okay, so once I've got that equation, it links p and t, but if I compare that to this, I can clearly see they want p equals. Okay, so the first thing I'm going to do is get rid of that ln and make it into e, so that's neatening it up a bit. The other thing I've noticed is that it says e to the kt, not kt plus some number, so maybe it's hinting that c equals 0. No, what it's hinting at is that plus c up there is not very neat. We can do something with this. We've done it once already, and it's worth you making sure that you know exactly how to do this part. So using my laws of indices, e to the kt plus c is exactly the same as e to the kt times by e to the c. Those two things are identical. Now, because they're identical, I can just rewrite them exactly the same sort of way. So the e to the c just there is just another constant. C value is just a constant, so the exponential function acting on that number is going to be just another constant value. But it's not very neat writing it as e to the c, so what I'm going to do is change that for a different letter, a different constant, which we're going to write as a. And as I said before, this is very standard. It's quite common that you will end up having to write it in this form. Okay, and I'll talk about why in a second, but get used to it. So if you don't understand those steps, re-watch it, make sure you get to understand exactly how that one comes about. Okay, so I've got my general solution, but I haven't finished answering this question just here. It's saying initially the population of the island is 50,000. Now the key word there is not the 50,000, it is the word initially. If we're talking about rate of change over time, initially is when time starts, in this case on the 1st of January 1991. So if we're looking at a situation where the initial value is 50,000, the t value is going to equal 0. Right, so I've got two bits of information there. I've got a p value and I've got a t value. So what I'm going to do is I'm going to substitute both of those in. If I substitute both of those into here, hopefully it's going to sort out one of the constants. And this is why it's important to rearrange it into this form. Because now that I've got it in this form, I notice that when I put 0 into it, this part here, k, can be completely ignored. Because k times 0 is just going to be 0. E to the power 0 is just going to be 1, not 0. Be careful. E to the power 0 is 1. So what does that mean? P equals A. So e to the kt, I've put the t value of 0 in there. That part there is going to equal 1. So therefore I've got my A value straight away of 50,000. And lo and behold, I can put that back in and get my general solution just there. Okay, so that's my general solution. The only constant I don't know now is the k value. It's still a general solution, of course, because I still have unknowns in there. So can I use that and hopefully answer the next part of the question? Let's have a quick look. The population of the island was 50,500 on the 1st of January 1992. From that, can you now calculate the k value? Right, so they're giving me this extra bit of information. And once I've got this extra bit of information, what I can do is I can do the same as what I did a minute ago and substitute in the two values. So I've got P equals 50,500, but the T value, let me just double check, is the number of years after the 1st of January 1991. Now this is talking about the 1st of January 1992. So that is just one extra year. So if I look at this situation, the T value is just equal to 1. Then the population is increased by 50. So I've got a P value, population, of 50,500. I'm going to substitute both of those back into that equation. Okay, so there we go. I've got my equation. I substitute them in, the T value, the P value. Obviously the 50,000 is always going to be there. So therefore I've got this. The only thing I don't know is K. Once I've done that, I got a k, e to the k is going to be 50,500 over 50,000. So my k value is ln of 101. Once I've got that value, of course, I got my k value, the three sig figs, and therefore I've answered this question. What is the value of k to three significant figures? I can also substitute that in for this constant just here, and then I've got my population equation sorted fully then. So there we go. I could go along and someone could say, what's the population at this time? Let's say the 1st of January 2020. So I could put that T value in. Okay, whatever the T value is in the case of 2020 would be 29, because that's how many years after 1991. And therefore substitute 29 into there and see what your population is going to be. And in fact, that's exactly what it asks you to do for part D. Calculate the population of the island in the 1st of January 2001. Okay, so in the 1st of January 2001, so that's 10 years afterwards, so I can use this as a prediction model. So 1st of January 2001 to 3 sig figs. So by the 1st of January 2001, we've got the T value equaling 10, it's 10 years after 1991, and we don't know what the population is though. But what we can do is we can substitute it into our new formula. So we're substituting it in just there for T, and once I've done that, the population is going to be 50,000 e to the 0.0095995 times by 10, and there we go. The population in 2001 should be about 55,200. Okay, so quite a big, long-worded question, but as I said, it's quite standard for you guys out there that's going to have to answer these questions to solve some applied maths problems. Okay, so have a quick go. I wouldn't say quick actually. Have a go at those exercises and take your time with them. Make sure that you've had a go at a massive variety. You'll be surprised that when it comes to your exams, the differential equations can often be some of the hardest questions on the paper. So it's always a good idea to make sure that you're practicing plenty of those skills.